as the only positive ion. Okay, why do we need this? Simply because whenever we have an aqueous solution, you will always have a few ions that is present, namely, right, H plus and OH minus. So what do I mean by that? Let's say we have let's say we have normal table salt. So normal table salt is sodium chloride aqueous. Later you receive the, so when you have aqueous solution, you will have two ions. Always you have H plus and OH minus. This coming from the water. And then sodium chloride salt has sodium plus and Cl minus ion. So when this salt here ionizes, you will actually get a couple of ions. I mean, technically, whenever we write ionization, is Na plus Cl minus. But we know that if you have a tank of sodium chloride, AQ, when you zoom in into the ions present, right, you actually have all these ions, H plus and OH minus. And the OH minus comes from the water. So you notice that there are actually two ions here. This guy also, this sodium chloride also produces H plus. When we define acid, we say that they are substances that produces H plus when dissolved in water. So this sodium chloride, normal sodium chloride salt, it also produces H plus in water, but is it considered an acid? Answer is no, because it has two positive ions. Positive ion 1, which is sodium. Positive ion 2, which is hydrogen. So by having two positive ions, this is technically not an acid. That's why the alternative definition is the one in red. The normal definition is just anything that produces H plus. Okay, so this is just a rough intro as to what kind of definitions you might see from your teachers. Okay. Ziyi managed to get this set, right? Ada also managed to get it.
I think I have this set.
Okay. Ziyi, yourself, you have it? Okay, good. Okay, let's go into proper for this. So in our equation, when we do ionize, when we are dealing with acids, we say that they will produce H plus in water. So you will always have the positive ion and the negative ion. So these are the few common acids that you will encounter in school. So just familiarize with this, because when in our written notes, in our written work later on, we will be writing all these equations together. So as of now, just know that these are the few common acids. Zikri, you received your hard copy, right? Have it? Okay, if you haven't have it yet, for today, you just listen through, and then I will send you the written copy after the lesson. Then you do your transfer over. Just make sure whatever we do today, you understand. Yep. Okay, so these are the common acids, formulas, and now I will give you the formulas of the 4 acids that is very common with us, with the text that you'll be doing. So nitric acid, formula HNO3, sulfuric H2SO4, hydrochloric HCl, ethanoic acid, CH3COOH. Tartaric and malic is not common, so I'm not going to do it. It's not going to waste energy. Okay, so generally, these are your common acids that you need to know. And do understand, acids are substances, when you throw them into water, they produce H plus ions. This was the same narrative that we had when we are doing bonding properties. We say that although they are like simple covalents, if you look at HCl, it is covalent bonding. How come covalent bonds, HCl, can conduct electricity? So when you are doing your test, we say this was due to the ability to form H plus and chloride ions in water. So as a result, they have free moving ions. So this is the same concept that we are looking at. Okay, if no issue, let's go on to physical properties. Okay, so over here there's a mixture of physical and chemical properties. And sometimes, right, when we were looking at properties, it's quite blur as to which are the properties that we will say take them to be physical. Okay, Clarice, in simple terms, right, what constitutes a physical property?
Physical changes.
Sorry again.
Physical changes.
Okay. And one of the things that we want to see is properties that don't link to a reaction. That means it's a non-reaction kind of property. Then we can classify under physical. So over here, the list, I will give you the few so-called physical properties, right? That is generally across many schools are accepted. So anything that don't deal with a reaction looks pretty good. So physical property, number one, sour taste. This is generally accepted. Able to conduct electricity, do an extension here in aqueous state. This is another good physical properties. Okay, so other than this, other things like turn litmus red, will it be a physical property or chemical property? Because very gray. Some schools accept this as physical, some schools don't. Okay, to me, my stand is right. When your litmus is basically a chemical, if you can cause a chemical, right, to change from blue to red in the presence of the acid must have reacted with the chemical to change its color. So as a result, I will not want to position it as a physical property because some schools may reject this. So we will ignore it, right? So we will not take it to be a physical or a chemical property. So physical properties for acids, I'll just take those two. Let's look at what are the ones that will classify under chemical properties. Chemical properties are reactions. So this is a very strong chemical properties. React with metals, number one, carbonates, number two, bases, number three, alkalis, number four. So these are your four chemical properties which align to their reactions. So chemical property is pretty straightforward. The rest of the stuff I will like corrosive, all this, very hard to categorize. So try not to do it. If I really have to categorize corrosive, I will put this as chemical property number 5. Litmus test, chemical property number 6. Okay. Any questions for anyone for reactions of, the chemical physical properties of acids? Okay. Next, let's look at reactions, chemical properties. So under reactions, we have those 4 reactions here. So very straightforward, acid, metal, salt, and hydrogen gas. To take note, right, not all metals can react with acids. Okay, so do help me write down the exclusion. Copper, silver, and gold. As a metal, they cannot conduct electricity. They cannot react with an acid. And the reason why they cannot react with acid generally is because they are unreactive. So basically, unable to react with acid. Copper, silver, gold. But of course, copper compound, silver compound, gold compound can, but the actual metal itself, no. Okay, how to get the equations out and all this, right? Again, we'll do it during our practice. So today is just to introduce to you the reaction types. So next, hydrogen gas test, I believe you all seen before. Test with a lighted splint, if hydrogen present, extinguish with a pop sound. This is a standard hydrogen gas test. This portion here, if you have not done metals, it doesn't make sense. So actually, there is a list that ranks metals from the most to the least reactive. So being the most reactive metal, they are able to react acid. So over here, those that the silver is actually over here, gold is actually over here. So these are the ones that are so-called not so reactive. So just remember as copper, silver, gold for the syllabus. Okay, how to get the name of the salts? We'll come to it again. So generally just know that salt hydrogen gas produced. Okay, all these are just examples. We can use it when we are doing equation writing. Today, I just want to show your theory. Carbonate reactions. So, not just carbonate, more accurately, it's metal carbonate. Okay, there's no such thing as non-metal carbonate. They are all metal carbonate, but just for the sake of it, it is reactions with metal carbonate, and you get 3 things over here. Again, salt is the usual thing, like carbon dioxide and water. So test for CO2, lime water, white PPT form when carbon dioxide present in lime water. Now, let me give you a few chemical names. Lime water has a chemical name of calcium hydroxide. So when we add in I believe this one you'll see before, right? Lower sec primary school, you all might say the lime water turns chalky. Okay, never use the term chalky again. Upper sec, we have to say white PPT form when lime water and CO2 comes together. Now, what's the identity of this white PPT? What is actually the white PPT? The white PPT is calcium carbonate. Formula CaCO3. This formula is Ca hydroxide. Okay, it's not given over here. Let me give you the equation involving lime water and carbon dioxide. Lime water is your calcium hydroxide, CO2. The final product you get here will be calcium carbonate. This is your white PBT. And you get water at the end. Okay, this is the white precipitate. This equation, I would say good to know for acid base. Okay, other than that, nothing much here. When you react with metal carbonate, you get three items: salt, CO2, and water. And do know the respective testing agent, their chemical formula, the white PBT, what is that, all those stuff. Okay, any questions for acid and carbonate reaction? Anyone have a question, please sound up. Okay, next. There's this thing about reactions with bases and alkalis. What exactly is the difference between those two? Okay, first off, let's decide what exactly is a base. I'm not going into the definition. I'm just showing you how to recognize them. They are, most of the time, a metal oxide. Or a metal hydroxide. These are defined, not say defined, you can understand or you can remember this as as bases. Then what exactly is an alkali? The alkali is linked more to the hydroxide. So if your hydroxide is soluble, if they are a soluble base, and they normally alkali will appear to us as a metal hydroxide. That is soluble. So this essentially breaks down, right, the difference between generally what is a base and generally what is an alkaline. It's all down to solubility. Okay, anyone, any questions regards to the difference between a base and an alkaline? I will show you an example what is a alkaline. I don't want to show you an example of a base because as long as a metal and oxygen together, the metal oxide is already a base, regardless of solubility. Metal hydroxide, they are all bases also, regardless of solubility. But the special category of alkaline, they have to be soluble in water. Soluble hydroxides, they are your alkalis. Okay, any questions so far? Those of you not using mic, if you all have any question, you all WhatsApp me. I think the Zoom chat a bit laggy for me. All right, let me give you some examples of what an alkali is. Alkali in syllabus. We have group 1 metal hydroxides. We also have lime water, calcium hydroxide. And the last one, not so common yet, but this particular alkali will come to you very frequently, very soon, is the alkali of ammonia. And we normally call it aqueous ammonia. Or we also call it ammonium hydroxide. Now notice this is a little bit different. It is not a metal hydroxide, but still is classified under an alkali. Okay, any questions regarding what is a base, how to recognize a base, and what is how to recognize an alkali? Okay, all right, sir. Okay, if no questions for this, let's look at okay, for this I will look at the equations together because there is a distinction between a base and an alkali. We want to recognize, right? For the examples over here, what are the reactants present? You see this work example number 1, we have, because generally when an acid react with an alkali or a base, you get only salt and water. So in this case, sodium hydroxide. This is a group 1 hydroxide. This is actually an alkali. It is also a base. Because remember, base is a metal oxide or a metal hydroxide. Both of them are bases. The broad base definition of a base. But because this sodium hydroxide here is a group 1 metal. So under the category of alkalis over here, we say that group 1 metal hydroxides, they are classified under an alkali. So this is actually an alkali and acid reaction or acid and base reaction. Okay, and then we get the salt and then we get the water. Okay, anyone, any questions identifying the alkali? Okay, if not, those of you still copying, give you a minute to jot this down. The rest can help me digest. Any question, please shoot. So while you are copying, what's going to happen for the next 1 or 2 months, right? Normally for this period of time, schools normally will do one of these 2 topics. Number 1 is either mole calculation, which is the calculation topic of chemistry. Number 2 is acid base. So my target is by the time school reopen, all of you should be done with this and mole calculation. Some of you already done moles. So those who are already done with your moles, you can, I'll be doing in-depth calculation with everyone, so you can join in also. I think none of you actually started on acids. So this will be our plan till the end of the holiday. So yeah, keep it first. So for now, I will just do acids first. Because for more calculations, there are many parts where you need to do equation writing that's linked to acids. So normally I have done this first. Okay, so the plan for these 2 months will be this. Some of you, your bonding, some of you still on bonding. I haven't do something. This one on the side, I will pull you out to do it separately. And if you have any other strange topics that your school is doing with you, just let me know. Otherwise, as a whole group, I will settle these 2 big topics first. Yeah. Okay, let's go to the next equation. Now you see this is a metal oxide also, and it reacts with nitric acid. Now notice this is not a hydroxide, and it doesn't fall under the category. Even if it's a hydroxide, right? It's not group 1. It's not calcium hydroxide, lime water. It is not ammonium. So generally, this, even if it forms a hydroxide, it will not be an alkali. So this guy here is actually a base. It's not an alkali. Simply because it's just a metal oxide here. Okay, so as a result, when they react, then you form salt and water, so to speak. Okay. So if you all can identify base and identify alkali, that's good. Equation number 3, because it is aluminum, right? I do not want to touch it because it has a very sensitive thing to classify aluminum. Aluminum doesn't classify like a base or something like that. End of the chapter, you will see. So I'm not touching example number 3 as an example. But of course, you should be able to identify that aluminum is a metal oxide. So it should react like salt and water as usual. Okay. All right. If not, let's look at this strength of acids. Give you all like 30 seconds to look at the graphic here. Oh, okay, wait, so I slow down a bit. Clarice, okay so far, right?
Yeah.
Okay, the rest of you okay? If you're lost already, let me know. Because it all stacks together. Ashton, okay for you?
Yeah.
All right. Okay, great. No, I just check in case I will fall asleep. Today I'm not doing any practice. We're just listening to story. Then the practice will come next week. Later you all fall asleep.
Oh no.
Hey, wow, you're guilty conscious. You admit first that you're not sleeping.
That's
Okay.
so pain.
Bloody hell, that one is confirm guilty conscious. Okay, let's look at strength of acid. So for the strength of acid, it says it's the extent of ionization. Okay, let's go back to the front portion again. What is ionization? So right at the beginning, we define acid as any substance that undergo the production of H plus ions. We call this process ionization of H plus or dissociation of H plus. So this HCl molecule, you see that it breaks down to give you H plus and Cl minus. This process is ionization or dissociation of H plus. So the question here says that the strength of an acid depends on the extent of its ionization in water. So in the syllabus, right, we have a few strong acids. Now this list here gives us all the strong acids that we require. So do remember these 3 acids as strong. HCl, sulfuric, nitric. These are your only strong acid in syllabus. Unless mentioned otherwise by your question. Otherwise, we will always take these 3 acids as the only strong acid in syllabus. And everything else is weak. As long as it's not these three metals, any other metals are considered weak acid. All right, so what's the difference between a strong and a weak acid? Strong acid, we say it ionized fully. Okay, over here it says ionized fully. Sometimes in your school, right, your teacher will say undergo complete ionization of H plus in water. Sometimes this is the narrative that school uses. So you can see over here, we have, as a sample, we have 3 HCl molecules. And the molecules fully ionized, all of them ionized to give you H plus ions. Now for a weak acid, over here it says ionized partially, which we also say they undergo partial ionization of H plus in water. So same thing here. This X is an unknown negative ion. So these 3 molecules are molecules of a weak acid. And you notice that over here, partially ionized, only 1 out of 3. Is it always 1 out of 3? No. This is just a graphic to show you. Is it always 1/3? Definitely not. Okay, so in the example here, you see that only 1/3 of the acid molecules ionizes. The 2/3 remains as the molecule. Okay, so the distinction between a strong and a weak acid is just everything ionized or some ionized. That's all. On its own, there's nothing to test for this. School normally wants you to, there's nothing much to test here. But its application is appears in many different topics. So generally, when you undergo complete ionization, right, over here, you are likely to have a high concentration of H plus ions because there's a large, or rather a complete ionization in water. Whereas for a weak acid, it's likely to have a low concentration of H plus ions. Okay, any questions, anyone, regards to strength? This one nothing much. It's just partial ionization, complete ionization. Those who are complete is the strong acids. Strong acids, we already got those 3 of them: hydrochloric, sulfuric, and nitric acid. That's all. Okay, let's go on to the next part. Later on, 8:30, we have a short break. If not, you all listen to long lecture, later fall asleep. 8:30, at least we'll have a short break, and then we'll come back again. Again, no practice for today. We'll do all this thing next week. So for acids, generally, that's about it. Okay, we are to show you something first. Yeah, let me find a space to draw something. Nice. Yeah, I'll draw it here. There's more space here. Okay, well, there's one reaction that appears quite frequently with regards to all this ionization stuff. So, for example, we have batteries attached to a light bulb. We have some conducting plates. And we have a solution here. Okay, let's call this solution A. Solution A. If it's HCl liquid state, we call this hydrogen chloride. Clarice, do you think this substance can, when it's substance A, will the lamp light up?
Yes.
Yes, because got H plus ions, is it?
Yeah.
Okay, remember we define acids as substance that will produce H plus ions in the presence of what needs to be present for the acid to ionize. Let's go back to this again. Let's look at the definition of an acid. Let's look at this portion here. What needs to be present in order for the acid to ionize? Sorry, Clarice.
Is it water?
Water, correct. You need, remember the acids, right? Or any of the molecules. If the molecule is supposedly an acid, right? It has to dissolve in water. And it must dissolve in water. Okay, it must dissolve in water. Otherwise, without water, right, they will not be able to ionize to give you H plus ions. Now, if you might ask me, why does it need to be water? Those doing A-level chemistry, your teacher will tell you. As of now, we don't need to know why, but we need to know water is essential. So without the presence of water, no ionization will occur. So Clarice, back to the HCl liquid state. Light bulb light up or will not light up?
No.
So the lamp will not light up. And what's your reason for this?
Because there's no H plus ion.
Yeah, because HCl liquid state, this is actually a simple covalence. And because of the lack of water, it does not ionize. To form H plus. So therefore, there is no free moving ions. Yeah. So if it's just HCl liquid, it doesn't happen. Now, what if it is something else? What if A is actually HCl? Now I let it dissolve in oil, ethanol, maybe paint, okay, any of this stuff. Ashton, do you think the lamp will light up? Now dissolve, previously not dissolve. Now this is dissolving. Will you light up?
No.
Why not? And you are correct. The lamp again will not light up. Why is that so? I thought we dissolve in something, right?
Is it like lack of water also?
Same thing, you're right. The question can throw you to say that you dissolve in anything else. Some students get caught by when they see dissolve, they straight away say can conduct already. But the fact is, you need to specifically dissolve, and it specifically must be in the aqueous state. Yes, Clarice, you're right. It must be in the aqueous state before ionization is possible. So the question can say you are this HCl or whatever acid, right, is dissolved in some substances. But if you do not have water, it doesn't work at all. So again, it will not light up because simply it did not dissolve in water. You notice I place a lot of emphasis on this because this thing every year it comes up, hidden in MCQ and all this stuff, and you try to throw us off. So try to ID this very strongly. You need water for it to be present. Okay, it did not dissolve in water. So again, there is no ionization. So because of no ionization, no free moving ions. Oh shit. Oh my God. Let me redo this. But anyway, it's already recorded already. So if anything, y'all can free screen to go and jot down anything missing. Okay, but so for the two solutions, I'll just put it in a nutshell what happens. Damn it. Okay, so we mentioned just now, if it's HCl liquid, the lamp will fail. Okay, after lesson, I'll go and free screen it, and then I will go and copy it and then send it to you all for this one. And then we say that if A is HCl present, that is dissolved, oh, Ziyi coming to it. I still got a few more scenarios. So when it's dissolved in, let's say, paint, oil, or whatever, okay, so again, nothing happens. The lamp will still fail. Now let's look at the next scenario. What if A is actually HCl dissolved in seawater, or let's say sugar water, or let's say salt solution? Do you think in this case the lamp will light up? No, this is not. Okay, I don't say anything first. You think it will light up? You said yes because okay, if I give you this scenario, right? Let's say this is HCl outright dissolved in water. Do you think this one, the lamp will light up? Very outright, this one. Do you think you will light up for this case? Yeah, this one is confirmed will light up because this is our usual wording. We say that dissolve in water, and then you have this, it will actually light up. Because in this case, we have the HCl ionizers undergo ionization to form H+. And therefore, now there are free moving ions. So either for this case, dissolved in salt water, sugar water, or this, do you think the lamp will light up either?
Wait, sorry, can you repeat your question?
This scenario, where we dissolve in seawater, salt water, sugar solution, all this stuff. Do you think the lamp will light up if HCl was dissolved in this solution instead of write out water?
Well, seawater is just a mixture, right? So
It's a mixture of what?
it's a mixture of salt and water.
Primarily salt and water, correct?
Yes.
So do you think the lamp will light up then?
Yeah, I think so.
Because
There is still there's still technically like pure water in
Hmm.
the
oh, definitely the water is not pure, lah, but you're right
Oh
to
yeah,
say,
well, there is still water molecules, yes.
correct. The
Yeah.
correct way is there's still water present. So as long as HCl is placed in water or any aqueous solution. So this part here represents any aqueous solution. The lamp will light up. Because as long as water is present, you will get ionization. Ionization of H plus, and hence you have, again, free moving ions. So the lamp will continue to light up. So very, very important, you always need to look out for water to trigger this property. You need water to be present to trigger the H plus. Okay, any questions from anyone? This one is slightly important. Okay. One more thing about this water thing. Just now we say that acid, right? When you use blue litmus, the litmus will turn red. The same goes for acidic gases. Okay, whether is it acid or acidic gases, when you let it interact with blue litmus, it is likely to turn red. Okay, so my next question is this. One of these setup, right? The litmus paper will turn red. Another setup, the litmus paper doesn't turn red. I literally just write this and then you see if you can catch it. I'm using HCl gas. I use blue litmus. Okay. I'm also using HCl gas with moist blue litmus. Kaylee, which of these two scenarios you are likely to see the blue litmus turning red? The moist litmus paper will turn red, or the so-called not moist version of it? Kaylee, what say you? The not moist one will turn red, is it? Actually, it's the other one. This one will actually turn red, whereas this one may remain blue. Okay, moist means water present. Kaylee, can you come up with a reasonable reason, right? Why do you think moist is required? when it interacts with, this is not hydrochloric acid, this is HCl gas. Okay, remember HCl is only referred to as hydrochloric acid if it's in the aqueous state. Anything else, right? HCl, solid, liquid, or gas, it is referred to as hydrogen chloride. Only in the aqueous state it is an acid. So Kaylee, why do you think the moist litmus will show a change into red, whereas the unmoist version doesn't? Yes. Yeah, so what Kaylee mentioned is that in the presence of the water over here, then the HCl gas can kind of convert into HCl as hydrochloric acid. So the concept here is water is required for ionization of H+, and it is this H+ that accounts for the acidic properties. That's why when you're doing experiments soon, right, in school, you will see that your teacher always asks you to moist your litmus paper. Because without moistening the litmus paper, your gas may not have enough water, right, to produce H+. And when the H+ is not produced, your litmus paper will not have a change because there is no acidic property. So in a nutshell, right, without water, right, HCl as a gas without water, it does not exhibit acidic properties. You need water to be present so as to trigger the H+, so the H+ can display the acidic property. Okay, please remember that. All sorts of typical acid behavior, right, is brought about by the presence of the H+ ions. That's why water is essential. So we have seen so far, right, from this example and the example above, in order to trigger the properties of the acid, like just now we mentioned, one of the good physical property is it can conduct electricity in the aqueous state due to the H+ and everything. So you need water to trigger the conductivity in aqueous solution. You need water to trigger the formation of H+, which will give you the acidic property of the gas. So without water, remember, acid will never behave like an acid. Water is essential for the formation of H+, which leads to giving you the acidic properties or the expected properties of the acids that we know. Okay, remember, if you cannot remember everything today, just remember water plus acid gives you acidic properties. Without water, not gonna work. Okay, anyone, any questions for this? Anyone wants to clarify anything before we go for our short break and you'll come back again? Okay, if no questions for me, you're gonna go drink water, go toilet, help yourself. Time now is 8:36. Let's be back by 8:40. Okay, when you are back, let me know. See you all in 8:40. Zikri, Ziyi, and Kaylee, are you back?
Yes.
Okay. Ashen, Adel, Paris, are you back?
Yeah.
Yeah.
Yeah, I'm back.
All right, let's look at bases. Totally different story from what we have been doing so far. Because these are the metal oxides and the metal hydroxides, all their reactions, everything all a little bit different. Okay, so generally we define them to be metal oxides. We also know that they can be metal hydroxides. So either way, it works. Okay, they will react with acids to give you salt and water. Again, how to get the salt? we'll do it next week. So pretty lame like that. I mean, these are just examples, metal and oxygen. Okay, as you can see here, most of them are insoluble, except just how we mentioned, group 1, ammonium, and also calcium hydroxide. These are the ones soluble bases. We call them alkalis. Insoluble bases is just insoluble bases. So bases that contain group 1 metals, ammonium, and also bases that contain calcium. They are all classic, they can all have the ability to form alkalis. So what actually happens? In fact, this one was one of those things, right? I was telling some of you when you are doing what do you call that? Ionic equations. Okay, let's take a look at what exactly how alkalis are formed. Okay, in a very simple way, when it dissolves into water, it forms a metal hydroxide, which is called an alkali. And of course, this metal hydroxide is soluble. Okay, you can see that this base here, every time we say that something is soluble, we put an AQ. Okay, we put an AQ. So for example, right, sodium chloride is soluble in water. So we put AQ over here. So this is actually correct. This is called sodium chloride solution. Now, before you dissolve it, it was actually NaCl solid. This is called solid sodium chloride. No fault here. But for a base oil, it's a bit different. You notice that when it dissolved, it was actually a solid, even though this is soluble. But we do not write AQ for this because, right? Okay, so let me put this down as sodium oxide is actually soluble. But why the state symbol is not AQ? That means why don't we just write Na2O AQ? This thing here. Okay, this thing does not exist. So when you write ionic equation, you have to be careful. Sodium oxide, although it is soluble, and we say that when it's soluble, the state symbol is AQ. But this thing doesn't exist because, okay, the reason why it doesn't exist is because when sodium oxide dissolves into water, it forms our alkaline straight away. So essentially, there is no such thing. It doesn't exist in an aqueous state. Compared to this normal table salt, sodium chloride. In a solid state, it was sodium chloride salts. When you dissolve, it is still sodium chloride. But the difference is that for soluble metal oxide, it was previously an oxide, but after dissolving into water, it turns into a hydroxide here. Now, if this feels confusing for you, then all I just want you all to remember is this. The state symbol for metal oxides, regardless of solubility, is solid. Always. So if you don't understand what I'm writing over here, okay, if you don't understand what I'm writing over here, not important at all. What I'm trying to explain is this. If you don't understand, it's okay. Questions never ask it, so we don't waste our brain cells. You just need to remember metal oxides. Their state symbol is always solid state. This is more important than the explanation. But if you can understand, it's good. If you don't understand, it's fine. Question, don't ask. Okay, please help me jot this down. Okay, so in a nutshell, what's important over here? Number one, bases are metal oxides or metal hydroxides. And if they are soluble, they are called alkalis. And the alkalis are the soluble OH. And then when you write the equation, state symbols for metal oxides, always solid. Okay, if you can remember this few, good enough. Okay. Help me jot this down. We'll move over in a minute. Anyone lost want to check with me anything before we move on? Just know that the oxide, when they dissolve, they form hydroxide. That's it. So same thing for lime water. Calcium oxide will dissolve into water, form calcium hydroxide, lime water. Something like that. That's why over here our example is sodium oxide is soluble, dissolve into water, form sodium hydroxide. That's it. Just remember the oxide is always a solid state. Okay, if it's all right, let's go to the next page. See, something similar again. Okay, the picture over there. Ashton, what do you think is happening to the sodium hydroxide when it's placed in water? Something similar to what we have done in acids.
Is it
Sorry, can you say again? You break off a bit.
is it dissolved?
It dissolves into water, and what happened to the sodium hydroxide when it's dissolved into water? It undergo.
It becomes hydrogen.
Okay, the hydrogen part is only for acids. But you see over here, what does it form? If you look at the picture.
Hydroxide.
Hydroxide. Hydroxide is the alkaline version of H+. H+ is for acid, and for alkalis, alkalis is exactly the same thing as the acid. Okay, acid in water form H+. Alkalis in water forms OH. So we can see that in the definition, they are quite the same. They are substances that produces OH ions when dissolved into water. Just now, we have the same narrative for acid. Acid are substances that release hydrogen ions in water, but alkalis, they don't release hydrogen. Alkalis release hydroxide. So we can also understand this as undergo ionization to form OH minus ions in water, or you can say undergo dissociation. Same deal. Exactly how acids produces H+ in water, alkaline produces OH ions in water. Okay, let you digest this a bit. Just now we mentioned that H+ is essential for the acidic properties. So if you remember the question they asked Kaylee just now about the dry litmus, without water, the acidic property cannot trigger. Without water, the conductivity property also cannot trigger. Same thing over here. Without water, the alkaline properties cannot trigger also. They are exactly same, but different. So we're back to the same experiment that we do just now. Same thing, the litmus have to be moist. Then you will trigger the OH. And for the lamp question, if I take the sodium hydroxide, I use sodium hydroxide liquid state, doesn't work. Sodium hydroxide dissolve into oil, all this doesn't work. But if sodium hydroxide is added to water, or sodium hydroxide is added to anything that contains water like salt solution and so on, your lamp will light up. Exactly the same, just change. Acid turns into alkaline. H plus ion change to OH. Their story is identical. Okay, so far, anyone, any questions? If not, I'm going to do the same thing here. Physical versus chemical properties. That you all take a look at this over here. You all check out this list. I'll go through in 30 seconds. Then I got a question to ask you. Oh, what say I lost everything, damn it. Okay, I'll go and rewrite it again. Annoying shit. Okay, so I wanted to go back to see just now all the how we label the physical and all the chemical properties. But since we lose it, let's draft this here. Physical properties. Either from the list over here, which one will be a good classification as physical properties of alkaline?
Soapy feeling.
Yep, number one, soapy feel. Any more?
Is ability to conduct electricity physical? I
Yes.
can't. Yeah. Okay. I think other than that, the rest is chemical.
Okay, so that's number two. Actually, we still got number three. The taste parts, if you all remember, right? Alkaline has a bitter taste. This is physical property number three. So this again is our three best physical properties for alkalis. If you go for either one of them, you should be okay. Let's talk about chemical properties. Chemical properties is definitely just reaction. So number one, number two, this is straight up confirmed physical properties. Chemical properties. So again, as we talk about litmus paper and corrosion, these two chemical, maybe chemical. This one may be chemical. If you really want to do it, this one should be our number three, number four, in order of which are the better ones. Okay, the best answers will be one. The larger the number, the one we want to avoid. Okay, so that's our physical chemical properties. Okay, for physical properties, this one is the same as exactly the same as the one in front. Acid base give us salt and water. So straightforward. Okay, anything from acid base? Nothing much, right? Okay. The one that we often forgot that it even exists is this reaction. For some reason, this reaction is almost always forgotten every year. Alkaline. Okay, they react with ammonium salt. What is ammonium salt? Okay, ammonium ion. This is the ammonium ion. So ammonium salts include things like, oh, ammonium salts here. Well done, it's all here. So this is the ammonium ion. These are examples of, well done, it's all here. No, you're right. Ammonium salts. Okay, these are the examples of ammonium salts, the chlorides, the sulfates, and the nitrates. Okay, so when they react, you notice ammonia gas is produced. Again, to construct the equation, all next week. But just know that this reaction is particularly important because this reaction is important because it is one of the very, very few reactions, right, that produces ammonia gas. This is one of the very few reactions that ammonia gas is actually given out as a product. So if we can't remember this reaction, right, then the question asks you, suggest something, react to give you, ammonia gas, will be lost really, because you can't think of any more reactions, because reactions that produce ammonia is pretty limited. So good to know this. Not say good to know, it's have to know. Okay, how do we test for ammonia gas? Okay. Ammonia gas here is, you notice this word here, alkaline gas. Okay. Again, difference between alkali and alkaline. Alkali is the noun. Alkaline is the adjective. Please do not use the wrong thing, because I always get things like the alkaline form is sodium hydroxide. No, that's an adjective. So you can say sodium hydroxide is an alkali, or sodium hydroxide forms an alkaline solution. See, that's the main difference. Do not cross over alkaline. They are not the same. I mean, it's quite straightforward, but somehow I still get the mix up between these two. So being the alkaline gas, it's going to turn red litmus. It's going to turn red litmus blue. So again, you notice here we use moist red litmus to test for this. Ziyi, what do you think the moist red litmus, the moist portion, why is it essential again? Why is it used to trigger? What is it used to trigger? Ionization of? Correct. Ionization of OH ions in order to observe the alkaline properties. Again, without water, alkaline not going to give you the property. Alkaline gases won't give you the property. Alkaline won't give you the property. You need, again, water to trigger the OH. Just like how you need water to trigger the H plus in water. Okay, so Give you a minute to consolidate this and help me jot this down before Apple screw it up again. For most of the school, if you can master this well, you can master mole calculation. When you reach your WA3, that should be the first deadly combo when these two topics comes together. And if it comes together, we are bonding. This
I
three,
die already.
this three is sure daily combo. Every year, my chem classes will all get filled up. The moment these two comes into, last time got mid-year exam. So thanks to bonding, thanks to acid, thanks to mole calculation, the deadly combo, well, a lot of people will fail. Now y'all don't have your real paper comes in end of the year. Most of you who are doing WA now, your real exam comes in end of year is an 80-mark paper, 50-mark paper, super long paper. It bundles everything up. That is the true mental of whether you can do well or not. All this WA is too tiny, right? And it's just a few topics. The moment we bundle up together end of year exam, that's the one that will test your true mental. But well, it's still some way to go. Please hard on to acid and mole calculation well. It will help you all to minimally pass your end of year exam. Okay, let's go to the next page. So again, construction of reactions we'll do next week. So you can see over here, most of them, they will form salt, ammonia gas, and water, and so on. So this one, nothing much. Okay. Strength, same sheet again. Ionized fully in water, also known as complete ionization of OH ions in water for the strong alkali. For the weak alkali, it will be partial ionization of OH minus ions in water. Exactly the same deal. Okay, so just now we talked about strong acids. We only got three. The three strong acids, HCl, hydrochloric acid, HNO3, nitric acid, and H2SO4, sulfuric acid. All these are memorized on. Other than these three ions, these three acids, any other acids we say, just classify them as weak, you're fine. Now for strong alkalis, okay, this list here a bit okay, some schools say yes, this is an alkali, and not some schools say it's not. Okay, I'll give you the universal one first. This one minimally you need to know. Then I give you the add-ons because alkali a bit awkward. Okay, in purple, you must know this. Strong alkalis in syllabus. Group 1 metal hydroxide. So you can see these two are group 1. That's why they are strong. No more really. That's it. Now, weak alkalis. Just now we mentioned there are three alkalis that I gave you. This guy and lime water. And the aqueous ammonia. Or the ammonium hydroxide. Okay, they are both the same. These two, okay, this list here, okay, whatever we have here is our standard strong and weak acid that you need to know. Sorry, strong and weak alkalis that you need to know. And it's very little only because unlike acid, we say that, oh, there's so many acids. So anything that's not those three, they are weak. But for alkalis, it's quite limited because not many of them are soluble in the first place. Because most bases, okay, most bases are insoluble. So the small group of them that are soluble, they become alkalis. So the small group here is what we have over here. Now, I'm going to add on, right, a few more that depends on your teachers. Technically, O levels, this is good enough. Okay, this is good enough. Okay, for O levels, you need to know this. This is add on by different schools. Okay, so add on strong alkali, no debate. It's only group 1 hydroxides. It's the weak alkalis that some schools add in a few more. The common ones that's added, number 3, barium hydroxide. This is another weak alkali. Okay, this is an add-on. This is a rare add-on. Magnesium hydroxide. So for magnesium hydroxide, okay, I just let you know that some schools says it is, but don't try to remember. Don't try to remember this. Very, very, very rare. Barium is much more common as an add-on. Okay, but other than this, the concept of the strength of alkalis is the same thing, partial and complete ionization. Okay, please help me jot this down. Anyone with question, please sound out. Okay. Right. Almost there already. Basicity of acids. This is only acids only. Controlling soil, okay, the controlling soil and types of oxide, right? Not doing today. Otherwise, it's content overload. I'll just settle the last part, basicity of acids. So what this says is basicity is loosely defined as the number of hydrogen ions that can be ionized in one molecule of acid. Now, sounds a bit far-fetched. But if you look at this, right, the two examples given to us is this. So you can see here, HCl, when it ionizes in water, it forms H plus and Cl minus. So over here, I have one molecule of HCl producing one H plus ion. So when the ratio is 1:1, this is called a monobasic acid. That's when you have one molecule forming one H plus. The dibasic one is actually sulfuric acid. So let's talk about H2SO4. In the presence of water, it forms H plus ions and sulfate ions. So from here, because of the 2, I'll have a 2 in front. This means that one molecule of H2SO4 produces 2 H plus ions. So the ratio here is 1 acid to 2 H plus. This kind of acid is called a dibasic acid. Di meaning 2. Okay, I'll show you one last one, which is a tribasic acid. H3PO4. Okay, this is called phosphoric acid. So same thing, it forms H plus. The negative ion is PO4 3 minus. So because of the 3 over here, I put a 3 in front of the H plus. So okay, we can see here, one molecule of H3PO4 produces 3 H plus ions. This is our only example of tri-basic acid. Only example. Okay, any questions for this? For those who have done mole calculation already, right? I normally won't refer to them as molecule, but you can see that for those who have, only for those who have done mole calculation, you can see that the ratio here is 1 mole acid, 1 mole H plus, 1 mole acid, 2 moles H plus. The ratio 1:1. Normally for quantity, if you have done mole calculations, if you have not done yet, ignore what I'm saying. So for those who have done mole calculations, most of the time we use this basicity in a mole situation. 1 mole produce 1 mole, 1 mole produce 2 moles, or for the case of phosphoric acid in green, 1 mole produces 3 moles. More accurately that way. Okay, so this is the concept of basicity. Depends on how many H plus you can produce per molecule. Okay. Any questions from here? Okay, if no question, I'll go and back check the video and then I will go and write it up again, especially for those who haven't received